Okay. Yesterday we discussed the normalization of wave functions. And what is meant by normalization? The normalization of the wave function means that the modulus square integration of the wave function over all space should be equal to 1. Natra. This is because the total probability of finding the particle in the entire space is unity. That is 1. This is called normalization of wave function. And we require this normalization of wave function because we give the interpretation of wave function as probability density. As this modulus square of the wave function is interpreted as position probability density, and since the total probability should always be equal to 1, this integral over all space is equal to 1. That is what we mean by normalization of wave function. And then we discussed an example. We discussed the normalization of this first example, and then example number 2 and example number 3 are left as your homework. Let me give you a hint. While solving example number 2, you will have to use the properties of gamma functions. And then this example number 3, the normalization of this wave function, you will come across this problem in unit 3 when you discuss the wave function of a particle in a box. So this examples 2 and 3, these are your homeworks. Next up, let me use the annotation. Wave functions should be normalized to unity if the probability interpretation is to be maintained. Let me make it full screen. So I repeat, wave functions should be normalized to unity if the probability interpretation is to be maintained. However, the plane wave does not satisfy this requirement. The plane wave. What is the expression for the plane wave? What is the wave function of a plane wave? The plane wave is represented by
e to the power
this wave function. Okay. So let me show you my whiteboard. So a plane wave so the wave function representing a plane wave, say for example in one dimension, is a e to the power I kx minus omega t. This is a plane wave. So what is this will be t. So what is modulus psi x t modulus psi whole square? This should be equal to psi star multiplied by psi. So when psi star and psi are multiplied, so what is psi star? Psi star is a, this will be a star e to the power I x minus omega t. And since we're taking the conjugate of psi, this should be e to the power minus I. Then multiplied by psi. What is psi? Psi is this. Psi is a e to the power I kx minus omega t. So this is e to the power minus kx minus omega t. This is e to the power I kx minus omega t. So here we have a minus sign. Here we have a plus sign. These two will cancel out. and what remains is only A star times A, and there is nothing but modulus of A whole square, where A is a constant. So for a plane wave, modulus psi square is equal to simply square of the modulus of A, and this is a constant. And this is a constant. So let me come back to my slide. So for a plane wave, in one dimension, this modulus square dx, this is equal to simply a square and dx. This cannot get here again. This psi square, this is nothing but a square. This is modulus of a square. So this constant modulus of a square, I can take it outside the integral sign, and what remains is only dx. So modulus of a square is taken outside the integral sign because a is a constant. What remains is only dx, integration from minus infinity to plus infinity. Here I go. Integration from minus infinity to plus infinity. And what is the value of this integral? Dx from minus infinity to plus infinity. What is the value of this integral?
Two times of infinity.
Infinity. So this integral is infinity. So this is infinity. This is infinity. Then yesterday, if you remember, I mentioned one thing. It was that square integrable. We said we talk about square integrable wave function. And when we say square integrable, what does it mean? It means that this integration modulus psi square d tau in three dimension and modulus psi square dx in one dimension, this integration should be a finite number. So square integrable wave functions are those wave functions for which this integration is a finite number. Infinity jadi hagibudo. See integration is finite number tau square integrable wave function kawi. So we have just seen that this plane wave, the wave function which represents a plane wave, this integration is not a finite number. This integration is infinity. So that means the plane wave is not a square integrable wave function. So since this integration is infinite, however, the plane wave does not satisfy this requirement since the integration on the left side of the equation is given by this, and since this integration is infinite, the plane wave cannot be normalized. Yeah, square integrable or integrally normalized the way they call. Similarly, the three-dimensional plane wave cannot be normalized according to equation 10, this condition. This mod psi square d tau, this cannot be equal to 1 because for a plane wave, this is equal to infinity. So there are two ways out of this difficulty. So what have we just seen? We have just seen that a plane wave cannot be normalized. So then what are the two ways out of this difficulty? There are two ways out of this difficulty. Let us discuss them one by one. And the first is to give up the concept of absolute probabilities when dealing with wave functions which are not square integrable. Instead, this mod psi square d tau is then interpreted as the relative probability of finding the particle at time t in a volume element d tau centered about the position vector r. So that the ratio mod psi square calculated at r1 divided by mod psi square calculated at r2 gives the probability of finding the particle within a volume element centered around R1 compared with that of finding it within the same volume element at R2. So mod psi square at R1 and mod psi square at R2 gives the relative probability. So gives the probability of finding the particle within a volume element centered around R1, centered around this position R1, compared with that of finding it within the same volume element at R2, at this R2. For the particular case of the plane wave, we see that psi mod psi square, mod psi square is nothing but modulus of a whole square. So there is an equal chance of finding the particle at any point. Since this is a constant, since this does not depend upon the position R, R1 R2 this mod psi square is always modulus of a square, which is a constant. So what does it mean? It means that there is an equal chance of finding the particle at any point. The plane wave therefore describes the idealized situation of a free particle having a perfectly well-defined momentum, but which is completely delocalized. Why do we say it is completely delocalized? Because the chance of finding the particle at any point is always modulus of a whole square, which is a constant. That means there is an equal chance of finding the particle at any point. R1 the particles laini having probability, so it is proportional to a square. R2 the laini having probability to a square. We take any point in space, the probability of finding the particle at that point is always a constant, and all points have equal probability of finding the particle. That means the particle is completely delocalized. And the particle has a perfectly well-defined momentum. The particle has a perfectly well-defined momentum because we can see from the wave function of the free particle that the wave function is given by a e to the power ipx minus et. Here p is the momentum of the particle. So this wave function representing a free particle has a perfectly defined momentum, which is given by p. Momentum is perfectly defined by, and single value it is p. So from the uncertainty principle, we know that delta x into delta p should be greater than or equal to h by 4 pi. So let me write the uncertainty principle here. The uncertainty principle says that delta x into delta p should be greater than or equal to h by 4 pi. So for a plane wave, the momentum is completely well defined, perfectly well defined. So that means for a plane wave, delta p is equal to 0. Delta p is equal to 0. So that means delta x equal to h by 4 pi. Sorry, this is not equal to, this is greater than or equal to h by 4 pi divided by 0. When I take delta p to the right hand side, we get h by 4 pi divided by 0. And any finite number divided by 0 is infinity. That means delta x is infinity. The uncertainty in the position measurement of the particle is infinity. And what does it mean? It simply means that the particle is completely delocalized. There is an equal probability of finding the particle at any point in space. Anywhere in space, to take a point, the probability of finding the particle is the same as at that point as compared with the probability at another point. So So the wave function representing a free particle is completely delocalized. This suggests a second way out of the difficulty. The second way is to give up the requirement that the free particles should have a precisely defined momentum and to superpose plane waves corresponding to different momenta to form a localized wave packet which can be normalized to unity. Aduna, second way is if we give up the requirement that the free particles should have a precisely well-defined momentum, and to superpose plane waves corresponding to different momenta, instead of defining a free particle as having a precisely defined momentum, if we superpose plane waves corresponding to different momenta, and if we form a localized wave packet, we superimpose plane waves with different value of momenta, and when we superpose them, we obtain a wave packet as we have seen yesterday. We saw yesterday how a wave packet is formed when many when waves of different wavelength superpose. Waves of different wavelength means different value of k, and different values of k means different values of momentum. So when waves of different momenta they superpose, they form a localized wave packet. And this wave packet does not have a well-defined momentum. So for a wave packet, delta P is not zero. Delta P is a finite number. So in that case, delta X is not infinity. Delta X is also a finite number. So we say that a wave packet can be localized. In such a case, if this wave packet represents the particle, then this wave packet which represents the particle, it can be normalized to unity. Yeah, because single plane wave already it cannot be normalized to unity, but if we say that a particle should be represented by a wave packet and not by a plane wave, then such wave packet can be normalized to unity. Okay, so this is how we try to reconcile with the difficulty that a single plane wave representing a free particle is not normalizable. Okay. Then we come to the concept of conservation of probability. Conservation of probability. Okay. And what does it say? First, we know that if a wave function is normalizable, then mod psi square. Mod psi square is simply equal to psi star psi. So psi star psi, the integration of this over all space should be equal to 1. So this is a normalized wave function. So if you are given a wave function and if you are asked to normalize it, then you check whether psi satisfies this integration, this relation. If psi does not satisfy this relation, then we multiply psi by a constant factor so that this relation is satisfied. Then next question is, what happens as time changes? We already know that psi, this wave function, it depends upon position as well as time. So wave function, this psi wave function J, this capital psi, this wave function, it depends upon position and time. So at a particular time, say let us say t1, at a particular time t1, you normalize the wave function. Psi is normalized already. Then at a later time, will the wave function remain normalized, or do we have to normalize it again? That is the pertinent question. The question is, once you have normalized a wave function, what happens as time changes? Because wave function depends upon time. Normalized wave function, after some time, will it stay normalized or not? That is the question. Because wave function depends upon time, it changes with time. So what happens with time? So once you normalize the wave function, will it stay normalized in future, or do we need to normalize it again in the future? So to find the answer, we look here. The interpretation of mod psi square as a position probability density requires that the probability of finding the particle somewhere must remain unity. It must remain unity as time varies, because the I repeat, the probability, the interpretation of mod psi square as a position probability density requires that the probability of finding the particle somewhere must remain unity as time varies, because we know that the total probability should always be equal to 1. Aduna, from the probabilistic interpretation of mod psi square, we require that once a wave function is normalized, it should remain normalized, because the total wave function, the total probability should always be equal to 1. This means that probability is conserved. This means that, I repeat, probability is conserved. In other words, once psi rt is normalized at a given time t, it must remain so at all times. That means once the wave function is normalized at a given time, it must remain normalized at all future times. The normalization integral, on the left of equation 10. Equation 10 is the same as equation 13. The normalization integral on the left of equation 10, 13, this one, psi star psi d tau. The normalization integral on the left of equation 13 must therefore be independent of time, namely d by dt of psi star psi d tau integration should be equal to 0. That means this integral should not change with time. Recall, this is psi star psi d tau over all space. It should not change with time. So d by dt should be equal to 0. Let us see how we can prove it. So here is the proof of probability conservation. This we call the conservation of probability. So how do we prove it mathematically? Okay, we can prove it here. Let us start by considering psi star psi d tau, where the integration is over all space. Here, I have not mentioned explicitly, but this integration is taken over all space. The rate of change of this integral with time is d by dt of integral psi star psi d tau. This is the left-hand side of this. Left-hand side. So we start with the left-hand side and we prove that it should be equal to 0. So let us start with the left-hand side. So d by dt of psi star psi d tau. So d by dt of psi star psi d tau. Next, next step. What is the next step? You take d by dt inside the integral sign. See d by dt is outside the integral sign. Now you take d by dt inside the integral sign. So what does it mean? Earlier, sigi expression meaning the expression meaning the meaning of this expression is, first you perform this integration. This is integrated over all space. So psi star psi, this is integrated over all space. So this psi star psi will not depend upon space, because this has been integrated over all space. Then psi star psi, it can only depend upon t, because this psi is a function of space and time, and since space has been integrated over, the final result of this integration will not contain any space dependence. At maximum, it can contain time dependence. First you perform this integration, then you take the derivative with respect to time. Expression. We can take the differentiation inside the integral sign. And what does it mean? we can interchange the order of differentiation and integration. That means we can perform the differentiation first and integrate the result later on. This is called differentiation under the integral sign. The differentiation under the integral sign. Let me show you new slide here. Differentiation under the integral sign. d by dx of f of x t with respect to t when from limits a to b. Limits is over all space, so limits is from minus infinity to plus infinity. So from a to b. So this d by dx of f of xt dt. You look here, the integration is with respect to t, and the differentiation is with respect to x. So if I take this differentiation inside the integral sign, this total derivative, it becomes a partial derivative. This total derivative, it becomes a partial derivative. So differentiation under the integral sign allows one to interchange the order of integration and differentiation. So integration differentiation have a say here. We are performing the differentiation first and then performing the integration later on. So this is integration, differentiation under the integral sign. So when you take differentiation inside an integral sign, it becomes partial derivative. So we are back. So d by dt, this is derivative with respect to time, and this is integration with respect to space. This is derivative with respect to time, this is integration with respect to space. So when I bring this inside, the integral sign, what will it become? Let me write it here. It will become, this will become integration over all space. This integration is over all space. Instead of total derivative, I should have partial derivative. Del by del t of psi star psi star psi d tau. It will become this. So when I take this differentiation inside the integral sign, this total derivative becomes partial derivative del by del t, then psi star psi d tau. So you perform this derivative first. Now psi star psi, this is a product of two functions. So you apply the product rule. First you keep psi star constant and you differentiate psi. I repeat, first you take psi star outside the differentiation and you differentiate psi star. Then you leave psi star outside the differentiation and you perform the differentiation of psi star. So this is what we have obtained. This is what we have obtained after applying the product rule of differentiation. So psi star thame and psi differentiate tore plus psi amuk thame, psi star differentiate tore. So this is equal to this. This is the intermediate step which I have skipped. This del psi by del t, how does a wave function change with time? Wave functions how does it change with time? So that the time dependence of the wave function psi t is not arbitrary, and it is governed by the time dependence Schrodinger equation. We have seen this earlier. How does the wave function change with time? As we have seen earlier, the wave function changes with time according to the Schrodinger equation. And the Schrodinger equation says I h bar del psi by del t should be equal to minus h bar square by twice m, the Laplacian of psi plus v of psi, where v is the potential energy of the system. So this del psi by del t, we have to substitute from this expression. And then del psi star by del t, how do we find this? It's very simple. We simply take the complex conjugate of the Schrodinger equation. When we take the complex conjugate of the Schrodinger equation, this IH bar, it becomes minus IH bar. So when you take the complex conjugate of any function, whenever you come across I have is it you replace it by minus I. The complex conjugate, whenever you come across I, you replace it by minus I. Whenever you come across a complex function, you replace it by its conjugate, so psi star. H bar is a real number. 2 is a real number. Mass is a real number, so it remains as it is. Laplacian operator is also a real operator, so it remains as it is. Then psi is a complex function, so you take its complex conjugate. This potential energy is a real number, so you leave it as it is. Then psi is a complex function, so you take the complex conjugate of psi. So this is how you take the complex conjugate of the Schrodinger equation. Aduna del psi by del t, so you divide both sides. You divide both sides by IH bar. So divide both sides by IH bar, you get del psi by del t, and you substitute that value here, Stubbs law. And then in this expression, divide both sides by minus IH bar. Minus IH bar is na side animal divide. You divide both sides by minus IH bar. You will get an expression, and you substitute that expression here. So del psi by del t na law. Sorry, del psi star by del t law. Del psi by del t law. Then you'll get the following expression. You will get this expression. Now using the Schrodinger equation and its complex conjugate in equation number 15, this is equation number 15. You have substituted del psi by del t from 16 and del psi star by del t from 17. So substituting from 16 and 17 in equation 15, you get this expression. Sigi expression. So this so 1 by IH bar. So when I take one IH bar towards the right, it becomes 1 by IH bar. When I take minus IH bar towards the right, it becomes 1 by minus IH bar. And minus, I can take it inside. Minus to the plus 1 granny, this is the minus 1 granny. So I can take from these two terms, I can take 1 by IH bar common and take it outside the integral sign, because I is a constant, H is also a constant, so I can take it outside the integral sign. We have this term here, and this minus is because of this minus sign, minus IH bar. So the plus line number say, because of this minus sign, it will become minus. So minus 1 record. So psi star minus H bar square by twice m del to psi by del to psi plus v psi. So the minus psi minus H bar square by twice m, Laplacian of psi star plus v psi. Then integral over all space. It should be integral over all space. So today on, then when you simplify this, so the v psi, when I multiply this by psi star, so I have this term. This becomes psi star v psi. Similarly, this becomes psi v psi star, and these two are the same. So these two will cancel out. So v terms this will cancel out. Then what remains is only minus H bar square by twice m, Laplacian of psi, minus plus H bar square by twice m, Laplacian of psi star multiplied by psi from the left, here multiplied by psi star from the left. So I can take H bar square by twice m. This is a constant outside the integral sign. So H bar square by twice m upon the putoro. H bar square by twice m upon the putoro. Then you also take the minus outside. So you minus sign, you take it outside. So you actually take minus H bar square by twice m outside. Then when you multiply both the numerator and denominator by I, it becomes IH bar by twice m. So you minus sign jiga, Sige, I square gi minus 1 duga cancel the one. So minus I h bar by twice m layer n. When you take out minus h bar by twice m outside, this becomes I h bar by twice m. What remains is psi star Laplacian of psi. So psi star Laplacian of psi. So minus h bar square by twice m is minus c. So what remains is minus psi Laplacian of psi star. So minus psi Laplacian of psi star. And this psi is simply a function. So I can either keep it on the left or keep it on the right. It doesn't matter. This is also a function. This is a function. So multiplication of two functions, you can interchange the order. So the left label size, I have kept it on the right. So there is no problem here. Then this expression can be simplified by using Green's second identity. By using Green's second identity. So let me show you Green's second identity. So this is the Green's second identity. I have a function psi and I have another function phi. So psi Laplacian of phi minus phi Laplacian of psi integration over a volume element integrated over a volume V. I repeat, so psi Laplacian of phi minus phi Laplacian of psi integrated over a volume U. This should be equal to psi gradient phi minus phi gradient psi dot ds integrated over the boundary of this volume. The boundary of this volume is a surface and it is represented by delta U. And since this is a volume, the boundary enclosing this volume or the surface enclosing this volume should be a closed surface. Only a closed surface can enclose a volume. So this surface integral is a closed surface integral. It's the circle of integration. So using this property, integration over all space. This volume integration, it can be changed to surface integration, and this Laplacian, it can be changed to gradient. So now using Green's second identity, the above integral can be transformed as this d by dt of psi star psi. This is the left hand side. Then I h bar by twice m. This constant is kept here. This term volume integral is replaced by psi star gradient psi minus gradient psi star psi, and surface integral taken over the surface S. And what is the relation between the surface and the volume? As I have just mentioned, this surface S should enclose the volume V. And what is the volume here? The volume here is all space. So in which the surface S encloses the volume of integration. And now this surface S should enclose all space. So this surface is a large surface whose radius tends to infinity. Whose radius tends to infinity. And this should be dot ds. It should be dot ds vector. In general, any square integrable function psi rt will vanish at large distances rapidly enough so that the surface integral of equation 20 approaches 0 as the surface of integration recedes to infinity. As the surface of integration recedes to infinity. So I repeat, here we have taken that psi, here quite faster, we have already taken assumed that psi is a normalizable wave function. Psi is a normalizable wave function means psi is square integrable. So for a square integrable wave function, this let me draw here. Any square integrable wave function psi t, it will vanish at large distances rapidly enough so that the surface integral of this, this surface integral, and where is this surface integral calculated? This surface integral is calculated at on the surface of this S. S hariba surface A. So the calculate whenever. And what is this surface? It is a huge surface whose radius tends to infinity. So at infinity, this psi star and this psi, they tend to 0. At this expression is calculated at infinity. And at infinity, psi star 0 ni, psi 0 ni, therefore integration of 0 is 0. Therefore, this right hand side is 0. So in general, any square integrable function psi rt will vanish at large distances rapidly enough so that the surface integral approaches 0 as the surface of integration recedes to infinity. Hence, since this right hand side is 0, what do we get? dy dt of psi star psi d tau is equal to 0. Hence, dy dt of psi star psi d tau is equal to 0 when this is integrated over all space. And the normalization of psi will not change with time. Thus, we have proved that a wave function which is once normalized will remain always normalized. And how is that expressed mathematically? Mathematically, that is expressed as the rate of change of size integral. The rate of change of this integral with respect to time is 0. Initially, what was the value of this integral? Initially, the value of this integral was psi star psi d tau was equal to 1 when the integral is over all space. So initially the value of this integral was 1, and now we have seen that this integral, the value of this integral does not change with time. The value of this integral does not change with time. That means the value of this integral always remains constant, that is 1. So the value z, integral value z, it will not change with time. This value, the value of this integral will always remain as 1. There is a wave function which is once normalized, it will always stay normalized. We don't need to normalize it again and again. That is the main idea. Okay. Then let us look at another interesting quantity, and this quantity is called the probability current density. Probability current density. The mathematical calculation is similar to what we have just done, so I can go a little fast here. The probability of finding the particle at time t within a finite volume V prime is given by this expression. Yarba? This expression. So let me, so first let me come here. Yeah. What is P d tau? P d tau is the probability of finding the particle within a very small infinitesimal volume element d tau. P d tau is the probability of finding the particle inside an infinitesimal volume element d tau. D tau never. So this is the probability of finding the particle inside a inside an infinitesimal volume element d tau scenario. And it is given by mod psi squared d tau. So this is the probability of finding the particle inside an infinitesimal volume element. Now, if I want to find the probability of finding the particle inside a finite volume element, so infinitesimal volume element, if I want to find the probability of finding the particle in a finite volume element, let us say this volume element. So volume element manungda particles probability what should we do? We should integrate this expression. We should integrate this expression over this volume, and this volume, it should be it can be represented by V prime. So if this is a finite volume represented by V prime, then the probability of finding the particle inside this finite volume V prime is nothing but integral of this expression over the volume V prime. So we'll also take the integral of this expression over the finite volume V prime. Infinitesimal hierarchy, this expression, only this expression is sufficient. But if we want to find the probability in a finite volume element, then we should take the integral of this expression over the finite volume element V prime. So that is the idea. So let me come back to my slide. Okay, here. It's here. So the probability of finding the particle at time t within a finite volume element V, within a finite volume V prime is given by the integration of this over the volume V prime. And this modulus psi square, it can be expressed as the product of complex conjugate of the function and the function itself, where the integrals extend over the volume V prime. This is a finite volume V prime. Now the rate of change of this integral with time is d by dt. This d by dt. Now I can take this d by dt inside the integral sign. It becomes del by del t. Then I apply the product rule. Product rule of differentiation, and we'll get this expression as we obtained in the last example. Psi star del psi by del t, psi del psi star by del t. This is similar to the last example, except that the volume here is a finite volume. Then this del psi by del t, I'll use the Schrodinger equation and substitute the expression here. And this del psi star by del t, I'll use the complex conjugate of the Schrodinger equation and substitute it here. Aduna, we'll get an expression which is similar to the last expression we obtained in the earlier example. So the complex conjugate of the Schrodinger equation is this, and so we use the del psi by del t from the Schrodinger equation, del psi star by del t from the complex conjugate of Schrodinger equation. Then we get this expression. Maniko, mamang the pangriwa example do some maniko. So d by dt mod psi squared d tau g derivative. Here the only difference is the finite volume element v prime. Otherwise, this expression is the same as the expression we obtained in the last example. Then this already same way that this v psi and v psi star. So this will be psi star v psi, and this will be minus psi v psi star. So this two will cancel out. What remains is only minus h bar square by twice m. This multiplied by psi star from left, and minus h bar square by twice m is multiplied by minus psi from left. Then I take minus h bar square by twice m outside the integral. It becomes minus ih by twice m. So sigi minus siga I, because of this minus, so because of this minus sign, the I which was in the denominator comes to the numerator. So it becomes minus mota I h bar by twice m. This is psi star Laplacian of psi. Psi star Laplacian of psi minus psi Laplacian of psi star minus Laplacian of psi star psi. Now, China koi Green's second identity sizinaba. Ado sedasu adu manai idea di toraku manai. Now we use the property of divergence. Divergence ki property to sizinare, and this expression is nothing but it is equal to this expression. See now, this we are using a property of divergence. Aduna sigi Laplacian j sigi psi star Laplacian psi minus Laplacian of psi star psi. This is equal to nothing but the divergence of psi star gradient psi minus gradient psi star psi. Then from Gauss theorem, this divergence of a function volume integral. This is Sigi Gauss theorem pandring ida ekoi amahana taurasi adudi karino haragadi this minus I h bar by twice m gradient psi star psi this expression multiplied by I h bar by twice m. This expression inside the bracket multiplied by I h bar by twice m, we call it minus j coroseva minus j minus j coroseva. This expression can be written as minus gradient of j times d tau minus gradient of j d tau. So this expression multiplied by IH is minus j. Minus j what will be j expression the now this term will come first and this term will come second in the expression for j. So gradient of psi star will come first. Where we have defined j as minus IH bar by 2m psi star gradient of psi minus gradient of psi star psi. Let me show it again. So this term inside the bracket multiplied by IH by twice m, this is minus j. So j is defined as minus of this. So we have obtained this expression, and that expression is del d by dt of mod psi square d tau is equal to minus gradient minus divergence of j d tau. Okay, next thus d by dt of mod psi square d tau is equal to minus divergence of j d tau. And this integration is taken over the same volume element v prime. Then we use the Gauss's divergence theorem. The above integral can be transformed into this right hand side. Divergence can be transformed to the dot product of a surface integral. Function amagi divergence lauraga volume integral lawasi asagi function dugi surface integral lobuga mani in a Gauss divergence theorem the tamkibula. So nothing is changed on the left hand side. What is changed is only this divergence theorem. We have applied the divergence theorem here. This divergence of j changes to j dot ds, and this volume integration changes to surface integration. And what is the relation between v prime and s? The relation is that the surface s encloses the volume v prime. V prime have a volume z enclosed to the surface to s never. And here this ds, it should be a vector here. Ds is a vector. So this expression is equal to this expression. That is the Gauss divergence theorem, where the surface S encloses the volume V prime. This equation can be interpreted in the following way. The rate of change of the probability of finding the particle in the volume V prime, which is given by this left hand side. The physical meaning of this left hand side is this. The rate of change of the probability of finding the particle in the volume V prime is equal to, then we have the right hand side, its physical meaning is the probability flux passing through the surface S bounding V prime. This right hand side, it is interpreted as the probability flux passing through the surface S bounding V prime. Therefore, the vector J given by equation 27 can be interpreted as probability current density. I repeat, therefore, the vector J given by equation 27 can be interpreted as probability current density. This idea comes from comparing this equation Comparing this equation with a similar equation in fluid dynamics. Comparing this equation with a similar equation in fluid dynamics. Fluid dynamics is a similar equation. You get a similar equation like this, and in fluid dynamics, this left-hand side, instead of the probability density, this is the number density of particles in a volume, and then this is the flux of this is the flux passing through the surface in a volume. I volume I have a container here. The container is manungda the number of particles. Fluid example ni a container container is manungda fluid khara lere. Sigi containers fluid number density, the number density of that fluid inside the container, it that number density will change depending upon whether there is an inflow of fluid or whether there is an outflow of fluid. Inflow itadi, then the number density will increase. Outflow organa, the number density will decrease. So this is the net flux. Comparing this expression with the similar expression for fluid dynamics, we get that this J can be interpreted as the probability current density. In fluid dynamics, this will be simply current density, and this should be simply number density. Okay.
So I see is electrostatics to compare to
Yeah. Electrostatics to compare to way. In electrostatics, this left-hand side will be nothing but the charge density. This will be the charge density, and then this will be the current density. J will be the current density. In electrodynamics, this will be current density. This will be charge density. V, suppose I have a volume V here. I have a volume V here, and this volume V is bounded by this surface S. This is V prime. I have certain charges inside this volume V. So volume V is the charges. Now some charges are flowing inwards. Charges then charges then if the inflow is not equal to the outflow, will the charge density remain constant?
No, sir.
Charge 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 density to constant or later. So the charge density inside this volume will change. So that change will be related to the net outflow of charges from the volume. Net outflow of charges from the volume. Net outflow of charges, that is given by the current density. So that net outflow will be given by this integral, and the rate of change of charge will be given by this integral derivative. This integral will give you the charge inside the volume, and this derivative will be the rate of change of charge inside the volume, and this will give you the net outflow of charge, and that is equal to that J here will be replaced by the current density, and this negative is because when there is a net outflow of charges, the charge density will decrease. And when there is a net inflow of charges, the charge density will increase. Adigi idea to niga. Adigi idea to loroga equina probability apply to what? Then this becomes to say electrodynamics charge density or in quantum mechanics, this becomes the probability density, and J the current density or now this becomes the probability current density in quantum mechanics. Okay. Equation number 28. Equation number 28. So this volume V prime. This volume V prime is arbitrary because when I introduce V prime, a finite volume V prime, I only mentioned that it should be a finite volume V prime. I did not specify its value. Masi 3 or 7 or 5 or have a magi value specified. I have only said that it should be a finite volume V prime. That means this V prime is arbitrary. This is arbitrary. Since the volume V prime is arbitrary, equation 28 can be expressed as this equation 28 can be expressed as you take this derivative inside, and then you neglect the you take this derivative inside. It will become partial derivative colony. And since this integration is over the same volume V prime, you can compare the integrand. Same integration J, same volume V prime V prime arbitrary. Now you can compare the integrand and say that the integrands must be equal. So del by del T of this should be equal to the divergence of this. Del by del T of mod psi square is equal to minus divergence of J. Or this del by del T of mod psi square. This mod psi square this is the position probability density. So we can represent this by P. Mod psi square is P represent the way. This is the position probability density, and you bring this minus divergence of J on the left hand side. This minus will become plus. So del P by del T is a plus, divergence of J is equal to 0. This is the usual conservation equation. If J is identified as the probability current density and P is the probability density. You have a similar equation for electrodynamics and a similar equation for fluid dynamics. In electrodynamics, this P will be rho. Rho, that is the charge density. This J will be the same current density J. Electrodynamics study, instead of P, instead of probability density, you will have charge density. Instead of probability current density, you will have simply current density in electrodynamics. Electrodynamics is equation, and this equation is called the equation of continuity. Equation of continuity. So in electrodynamics, this is called equation of continuity. In fluid mechanics, we also have a similar equation of continuity, and in quantum mechanics, we also have this equation of continuity. And this is the usual conservation equation. If J is identified as the probability current density in one dimension. This is in three dimensions. In one dimension, this can be expressed as in one dimension. This divergence this divergence will become del J by del X. And this P, the rate of change of P with time P, which was initially a function of X, Y, Z, now it becomes only a function of X in one dimension. This is in three dimensions, this is in one dimension. And in one dimension, the expression for J. J expression let me show it to you here. The expression for J here. This is the expression for J in three dimensions. In one dimension, this gradient will become simply del by del X. This will become simply del by del X. So in one dimension, this J is simply minus I h bar by twice m psi star del psi by del X minus del psi star by del X psi. If I bring minus I, if I bring minus and I together, then I can bring this I on the denominator. Sometimes I multiply both the numerator and the denominator by I. I multiply the denominator becomes 2mi and the numerator becomes I square. And what is I square? I square is minus 1. So minus 1 go minus siga plus olega. So this simply becomes h bar 2mi divided by h bar divided by 2mi. C expression here I have simply multiplied both numerator and denominator by I. The term inside the bracket remains the same. So let me stop the recording here.